Hello everyone, my name is Mohamed, and I'm here to tell you about the work we do at EXO around privacy in the context of AI. So at EXO we work on democratizing AI access, and what does that actually mean in practice? One definition is frontier models available to everyone. That some of the best models in the world are just like open and available to use. And the reason why that's hard is open source software is very different than open source AI. In open source software, you just need a laptop and good ideas, and you can make progress. Open source AI is a lot more like hardware in the sense that you need massive upfront capital to make a dent. One example of a frontier model is Llama 405B, developed by Meta. And that model was trained in a gigantic data center full of these H100 GPUs. I think Meta has around 600,000 at the moment. But even if Meta does great work in training these models and making them openly available for free, it's still very hard to use these models. So the model just mentioned is called Llama 405B because it has 405 billion parameters. So it's like hundreds of gigabytes. So just to use that model, I need typically like a rack of these GPUs. And an H100 is roughly like $30,000. I'm not sure about the people here, but I don't have like 5 of these lying around in my house. So at EXO, we work on like making it really easy to solve these problems by literally allowing you to aggregate consumer hardware. You can literally grab a bunch of MacBooks or phones or Linux machines or whatever, and you can run the most powerful models in the world. So typically, when I run it, it looks like this. I can just connect a few Macs together. It should be very easy to set up. Takes like a minute, just one command on all these Macs, and everything gets figured out for you. And then you can run these powerful AI models. For example, there's a video featured by Meta of my co-founder Alex running Llama 405B, which was like the biggest open source model in the world. And I think there's a video of it, if it actually works. Oh.
On my 2 MacBooks. So it's a 405 billion parameter model, which is 4-bit quantized, so it's about 200 gigabytes that is split up between these 2 MacBooks. And you can see that it's a larger model, and it's actually being a little bit sarcastic to me in the responses, which is something that I haven't seen from these smaller models. Apparently, this is on par with the best closed source models.
So
I just got the new Llama running on my 2 MacBooks.
In this case, like the model you're running is just a very simple chatbot, which is not super interesting. But you can run like very complicated things on it. Like if you go to the next slide, and the second link, yeah. Here, you can have the exact same setup. We're running something called Open Siri, which is like a local AI version of Siri that's fully local on your device and fully private. So here, Alex is asking Open Siri to schedule a catch-up call with me. And Siri is saying, well, all your personal machines, as in your iPad and your laptop and your phone, are being combined in a local cluster that's fully private to run the Open Siri. And what's going to happen right now is Open Siri is like a collection of a bunch of machine learning models. One of the models, like looking at the screen, it's a vision model. It's literally like swiping through your laptops and carrying out the computation that it's supposed to carry out. So there's a model that's like planning. It stops. You see the thing called automation running. It's like looking at the screen, like a screenshot, and then analyzing what to do. And here's like, going to my calendar and scheduling a catch-up call as instructed. And yeah, like again, this automation running, it pauses to analyze the screen and then it just carries out. So here it's like, it can look up stuff from my address book, the emails of people that I have and so on, and carry out all the tasks. And then I think at the start of the video, Alex says, do you want me to DM him? And it says yes. So now after getting the calendar invite, it's gonna go and like send me a message, hey, here's the calendar. Yeah, it's still a bit slow, but. Yeah, and then finds me on Telegram. And just sends a message with the actual invite. Anyways, yeah, so we can go back to the slide. So this is one example of something that I personally would never want to have on like a server somewhere. It has access to all my contacts, my messages, my everything and so on. And so far everything is fine because everything is just running on premise, right? Like there's nothing being leaked anywhere. Like everything's just running on my own machines, it's all local. So I don't have any privacy problems. But this setting of like just running things on premise doesn't always work. And that's where, surprise, surprise, FHE comes in. For example, in the settings we've just seen, like a chatbot or like an AI agent that's like doing something locally, it's like a single player activity. If I have like a game or an exchange or confidential ERC20, transferring money, these are things I can't just do on my own machine offline. This is something that touches multiple people, and then you can't just like do it locally on premise. The second thing limitation have, with all the stuff we've done, so that you can do with Extra right now is, you can only use open source models, because the model needs to be open, because you have to download it and use it yourself on your own premise. Which again, is a big limitation, because many good models are like closed source. And the last thing is like that the results of all these things are kind of offline, or it can be public and private at the same time. So to extend the things you can do right now with EXO, which is your local AI devices clustered together, is you can use some form of encryption, where I can send a query to some server somewhere or another MacBook or another colleague, and I'm running an AI model somewhere. And just like on a very high level, all I care about is like there's a bunch of matrices being multiplied and nonlinear functions. That's essentially what a machine learning model is. So there's like some just very high level stuff. The setting we operate in, the TLDR, is you typically have something like this, which is there's matrices, so I'm multiplying and adding stuff up. And then the big yellow thing is like a nonlinear function, which is most of the problems come from that, as we will see in a bit. So really what I'm doing with any AI models, they're all variants of the same thing here, which is I have layers, and each layer is essentially a bunch of matrices being multiplied and then a nonlinear function. And that's it. For example, in this specific case, I can have a neural network, a machine learning model, that takes an image, like a handwritten digit, and is supposed to like tell me, is this which it is from 0 to 9. So again, all this is just matrices and nonlinear functions. And in practice, what I do is I have this thing called hyperparameters and then parameters. Hyperparameters are, for example, how many layers there are in a model. Like when I'm training a model as an engineer, you think about, okay, how many layers do I want? How deep is each layer? Which nonlinear function should I use? Should I impose some structure? For example, I could like impose a structure that these matrices should be at least 50% zeros or something. These are all like hyperparameters. So once I decide the hyperparameters, typically what you do is you go and train a model. You give it some data, and you find the best like individual numbers in those matrices. That's really what I'm doing. So TLDR is a bunch of matrices and nonlinear functions. You typically try to design these models, how many layers, which nonlinear function, and so on. And that's the hyperparameters. And then you go and train the model and find out the parameters. So what we do with FHE is this thing called homomorphic encryption aware training. So normally, when I was first trying to do this, I just had quote unquote regular training. I'm just training a model, like let's say to classify images. It looks at handwritten digits and gives me which digit it is. I just train a model. And then after I have a model, after the model is finished, when I'm using it at inference time, I care about some setting which I care about privacy. Like I'm sending something to a server and I care about privacy, so I want to encrypt my query. So I just train the model without thinking about FHE. And then once I have the model trained, I want to use it, then I'm thinking like, how do I design this? And intuitively, when I was working on this, and a lot of people always work on this is a little bit iterative. Like, given how the models work, you might make some tweaks to the model itself, such that when you use FHE, it's a bit faster. And Heat essentially formalizes that and allows you to do it in a very principled way. The idea is essentially at training time, I'm not encrypting anything, but I'm keeping in mind the inference time cost. And then at inference time, I have like a very simple search over schemes, and kind of what you hope to get is like a model that's like slightly less accurate, but much, much faster. So just to hopefully make this very clear, normally, if I'm just training a model, like an image model, I have a bunch of images. I'm trying to like predict what the right number is, for example. I have a loss function. I'm just training the model to find the best parameters. So I'm trying to just train the most accurate model. That's it. What Heat is essentially is the loss function, the thing you're minimizing, is the normal loss function of the accuracy plus alpha times some FHE loss, which essentially is how expensive is it to like do the inference at FHE time. So what this alpha thing does is, if it's 0, then I'm multiplying by 0, so the loss is just the normal loss. So it's just normal training. What that's saying is basically, I don't care that much about how expensive the FHE is going to be later. But if alpha is infinity, that's saying I only care about FHE, and the model can be just 0 accuracy. So actually what happens is like, if you set alpha to infinity or like a very high number, you end up with a model that's completely useless. It doesn't predict anything accurately at all, but it's very fast when you do FHE on it. And really in practice, you want a middle ground, right? Because if it's 0, then nothing is happening, it's just normal training. If it's infinity, then you get like a trash model that is fast to inference, but is useless in practice. So just to try and visualize this, these are the two things we care about. There's the loss of like the accuracy of the model. So again, the higher this is, the better my model is. So if it's an image model, I'm better at classifying images. If it's some transformer, it's like GPT-5 instead of like GPT-2 or something. So like you want this to be as low as possible. But typically, the lower this is, the more complicated the model is. So you end up, when you use it in FHE setting, it's like a lot slower, literally. Like, as in it would take, I don't know, maybe an hour to infer instead of a second. So the holy grail is like you get something that's like low on both. It's just like very, very accurate, like low loss here, and like very easy to inference. So just some points here. Like the red dot here is high loss and L2 and high loss and LFHE. So it's like both like not very accurate and not very fast. So when I'm comparing like what kind of stuff happens here, like the green dot is just Pareto better. It's better in every dimension. It's like both faster and more accurate than the red dot. So that's an easy choice. The more tricky part is like, which one is better? Is it like the yellow dot or the blue dot? Well, there's no clear answer what's better. It depends on like which value alpha to choose. Essentially, if you pick the blue thing, you're saying, I care a little bit more about the FHE cost, so I'm willing to have higher loss on the training, so less accuracy. And yellow is, I care more about like the model being accurate. So it's a bit of a trade-off here. And when you run this optimization, just like when you do normal machine learning, but you run these optimizations, you have this like much bigger space you search over, and essentially just training off like accuracy and performance. So this is like something that's, you can just like run and loads of different models and see what comes out of it. So one interesting finding, there are like a bunch, but I'll just focus on one for now, is what ends up happening a lot is you have these things called ternary models. So it's a model where normally in a normal model, the matrix can be anything. This could be, I don't know, 16.78, whatever. It can be any floating point number. But ternary models are models where it has to be 1 minus 1 or 0. So that's a structure that I impose on it. And what ends up happening is these models end up being like less accurate than like general models, but they're not that much worse. It's like 2 to 8% lower accuracy. But that model plus a ReLU plus a very specific kernel ends up being like 113x faster than like a regular machine learning model. So again, I'm just training a model. Normally, if I'm training a model, I just find the most accurate model, and then later I think about FHE. Here, while I'm training the model, I take the FHE loss into account, and I iterate over all of different configurations of the models, and I find one that's like the right balance for me. So this is a really interesting thing of like, I can have like a very accurate model, and it's very slow, or I can have a model that's like, let's say 2 to 3% less accurate, slightly less accurate, but it's like 100x faster. So yeah, that's basically the TLDR of heat. Like, generally, I think about privacy a lot, and in terms of like single player models, like a chatbot or something, the easiest thing is just like run it on premise. Just run it on your own machine, nothing needs your device, everything's good. And everything's private. But the second you want to do anything that's a bit more collaborative, like let's say I have an LLM and I care about having up-to-date information from the cloud, like what is the weather like today? My local model doesn't know what the weather is like today because it doesn't have access to any external information or databases. So there I can just, or I would care about a closed source model, there I could use FHE to guarantee privacy even when I leave my own premise. And one way to like efficiently balance the accuracy and the inference time cost is to use something like heat, homomorphic encryption aware training. Again, you're not doing any encryption during training, you just are aware of it. You're keeping it in mind your loss. And essentially it just helps you find like the sweet spot where, okay, I'm gonna get a model that's like slightly less accurate, but it's gonna be like this much faster. That's it, thanks so much.
Do we have any questions? Can you give him a microphone? Actually, say
that. Hi, yeah.
Yeah.
I just want to know what does the LFHE, the loss function look like?
Yeah, so it depends what you're optimizing for. Like, I left it out because it can be a bit complicated. you could be optimizing for latency, you could be optimizing for like throughput and so on. But like one example could be literally the latency of the model. So you generate a bunch of like random configuration, you inference it 100 times, you take the average time, and now you know how fast it is to inference that, and that becomes a loss function.
Okay, so that is like tunable, is it? Like the type of loss that you put in?
Yeah, so like sometimes you're optimizing for latency, right? Or throughput or energy or something.
Okay.
So it can be it can be specific on what you're trying to do, but it is some kind of loss that's related to FHE when I use it. So the simplest thing is literally how long does it take?
How fast is it or something
Yeah.
like that? Okay.
So
I have two questions. The first one is, you mentioned that it's 113x using ternary. If you go to the performance numbers there, if you go back a bit, yes, it's 113x speed up compared to vanilla concrete ML. Is this an FHE or is this like normal kernel that you use in the world?
so both cases are using concrete ML, like Zana's library.
okay, I
It's
see.
just like in one of them, I'm just picking a different model. It's not like I have a new solver or anything. It's just like I have a different matrix.
I see. So the model, okay, I see. So a different matrix, and with ternary matrix, you get 113x speed up. That's what
Yeah,
you're
a
saying.
ternary matrix with a specific way of carrying the operation, and you get like a massive speed up,
When you,
but
when you
it's
say
less accurate.
Sorry, when you say specific way of doing that operation, what do you mean?
So, like, one of the main reasons why this is faster is I don't actually multiply anything.
Yeah.
Because multiplying by 1 is just addition.
Yes.
Multiplying by -1 is subtraction.
Yes.
0 is omission. So the naive thing, you would like multiply by 1, or you can just add. So you have to like encode that logic that when it's multiplying by 1, don't actually multiply anything, just add it up. So like you write like a short script to like keep that inside of mind. This also like is so another example of something that's worse in both dimensions, that's like slightly worse, is binary models.
Yes.
So here you only have 1 minus 1 or 0. I get the exact same property if it's just 1 and 0, right? Because 1, if I multiply by 1 is addition, 0 is subtraction. I don't have any multiplication either, but it's like way less accurate than just adding another component, which is -1. So binary models are only 2 values, ternary is 3 values, and ternary is like a big step up in accuracy. So when you're looking at like, where do I want to be in this diagram? Like the ternary one will be just like significantly lower in terms of loss, because it's like a lot more accurate. And it's like just slightly slower.
I see. And the L2 here represents the loss in FHE because the
No,
activation-
the L2 here is just like the normal loss.
The
This is
normal
FHE
loss. Okay, I see.
So if I train like a very normal model, the loss will be very low.
Yes.
Ternary one is slightly higher loss, less accurate, and binary one is like a lot higher, right? It's like a lot less accurate.
But there's also, I suppose you're taking that into account in LFHE, but there's also a loss that happens when you evaluate a model, a normal model in FHE, right?
Yeah, assuming
Yeah.
it's the same thing here.
Okay, okay, I
right?
see.
Like, what am I actually inferencing at FHE time? Any other questions?
Awesome. Thank you very much.